Welcome to Lecture 8. Today we'll be covering the equilibrium in kinematics. The equilibrium equations were covered in Lecture 7, but I will be doing a quick summary of that, and then I'll jump into the kinematics. Today we'll be covering the Chapter 2 still, and that's in my book. And if you recall, we looked at the overall equilibrium of a body. We had traction forces being applied, we had body forces being applied, and we can even have accelerations being applied. Here in this particular lecture notes, I didn't have them at the time, but you could have acceleration as well, no problem. And that acceleration is acting on a volume of material as well. And then we went in and did the overall force equilibrium of the body using the three Cartesian directions, where the three Cartesian directions, and here I have set AI equals 0, but in the previous lecture we didn't. And this is true for I equals 1, 2, and 3. So X, Y, and Z, in other words. And so hopefully that is clear to you. And then we looked at the moment equilibrium equations about the origin, which is given by this equation. And again, I could have done the R cross rho AI as well, but I didn't include that term, which is fine. It's okay for what I do here. And then we performed the overall equilibrium. We converted everything into index notation because it's a little bit easier. So that's the one I did here, equation 2 here. One thing I want to point out in my lecture's notes, I was showing you that Ti equals sigma ij and j. In the past, I have taught it so that j is in the second index, but in reality, these two are the same because the stress, and by the way, tau here is sigma. I used to use tau. It doesn't matter because at the end of the day, the stress tensor is symmetric as long as the conservation of momentum is maintained. If you substitute the Cauchy's relationship here, and V is the normal. Now I changed the notation. In the previous lecture I used N, but V is also used as a notation for that. That's the V is the normal to the surface. Then this is a force, summation of forces should be equal to 0. And when you do the calculation, then you get the equilibrium equations. And somebody asked me, well, should be IJ or JI, like I have it here. JI is fine and IJ is fine because the stress tensor is symmetric. And we know that from the conservation of angular momentum. And so this is always true when the conservation angular momentum is maintained. And for that reason, we do find that when you expand this conservation angular momentum equation, when you expand that and you work it through, you will find that this right here, and we demonstrated, is that the stress tensor is symmetric. And so from that perspective, that's what we covered. Well, we talked about the idea of stress. Stresses are those components, are those forces inside the body that react to external forces that are applied to the body. And those stresses will help us later on to predict failure. Most importantly, we also then figure out a way of relating the traction forces to the stresses inside using Cauchy's relationship. We came up with the idea that the stress tensor is symmetric. So there's only 6 components of stress that really matter. 3 of them are diagonal, 3 of them are shear that cause the cube to distort, while the 3 components are diagonal, cause the cube to stretch in all 3 directions or compress maybe. We also talked about the idea of max principal stress. We talked about the idea of Cauchy's reciprocal theorem. And then we talked about the equilibrium equations that I just quickly covered for you to show you a different convention that I myself had thought before, and I have forgotten that I actually did that. So I apologize to those that who I told them, well, this is the way it is, but well, no, I apologize because I've taught it the other way as well. And the story behind that is that there are various approaches that are used in industry. It's just something to keep in mind. And different books will approach it differently. And you will find authors from different books. A particular author could even change convention when it goes from book to book. You will see that from various books. Bottom line is, it doesn't really matter. The stress tensor is symmetric. And so at the end of the day, we are good to go. Today, what we want to talk about is the next step into the understanding of structural mechanics. So today I'll be covering the strain deformation mechanics. And to talk about that is, why do I care about strains? It's because a structure deforms. You know, a structure deforms when you load it up. If I'm standing on a diving board, that diving board will deform, will deflect. The deformation will change the dimensions of the body. It will change the shape. Deformations do induce strains throughout the structure. And so what is strain, we'll be talking about that, but the strain is defined as a measure of the relative deformation of the material, and it is directionally dependent. And so strain, you know, measuring relative deformation makes sense. I'll show you a picture very soon. Because just by, if you see something deforming a lot, it doesn't mean there's a lot of strain. I'll show that in a second. Strains can be measured using gauge clips or digital image correlation method. And there are ways to measure it when you test it. That is the advantage of really understanding strains, because if you can measure it, then you can correlate it to your models. And strain is a really nice measure. It's a direct measurement of the deformations within the body. On the surface of the body, I meant, because you cannot really put a strain gauge inside the body. You can put it on the surface of the body. The deformation patterns for solids and deflections can be visualized. That's the advantage of really using strain and understanding strains. By contrast, the stresses have to be determined indirectly from measuring forces, or by other methods that are not, you know, they're indirect. They're not direct measurements. So strain has really a nice advantage there. Here you can see an aircraft, a Boeing aircraft being tested. Well, guess what? Over here, over there, this at the tip of that wing, you can see a lot of deflection. It doesn't mean that you have a lot of strain. It's most likely the highest strain occurs about here. And so, you know, maybe this strains could be lower here. Just because it's deforming a lot doesn't mean that deflecting a lot doesn't mean that the strain is the highest there. In this case, the strain is the highest probably over here somewhere in this area. So again, that's a wing that's loaded. In every aerospace structure, every airplane has to go through this rigorous test. You can see a lot of deflection during this test, and you'll be surprised, but these wings can take up to 30, 40 feet of deflection without failure. So yeah, large deformations can occur, but strains could be small at that location. Maybe the strain is largest at a different location. And so you have to really, really understand what strain really means before making those assumptions. So let's go to the next slide here. The deformations can be, you have several ways to look at deformation. A body can go under rigid body rotation. It can translate, that can happen too. Here you can see how rotation occurred. So it deformed first, this body deformed first. You can see it here. It deformed to this shape, kind of distorted, the circle became an ellipse. And then this particular body, we can see here that it had to distort first. So I can decompose the deformation into distortion, it distorted. And then I can take this distortion and rotate it. You can see that there is rotating right there. And then not only that, maybe perhaps I have this body translating. So the deformation mechanics of a body can be decomposed into distortion, rotation, and translation. Rigid body rotation, rigid body translation, and then distortion. So that can happen. And so it's important to understand. Now, I did forget to mention that I could have distortion along with stretching. Not just distortion, but stretching. So for example, I have a square, that square becomes stretched. That can happen as well. So something to consider. Here you have another example of an undeformed body going to a rigid body rotation. And here you can see stretching or compressing here. And here is stretching in the different direction. And then here you have shearing. Okay, so you can see how shearing is accompanied by deflections, by angular changes. So this is 90 degrees. and the angle changed. Here, the angle did not change when they're stretching, but the length increased. You can see that here and here, okay? So yeah, it looks fundamental, but it is interesting, and it could be complex. Um, Another point I want to make is that when you apply a load, you will get a deformation, and that deformation can change and vary depending upon where you are. Here is almost square, nothing much, but you can see a lot of deformation over here, distortion, things are changing. So that can happen, and you can see a lot of deflection here. It doesn't mean the strain is high here. Maybe the strain is very small. Who knows? That's something that we will have to understand better. So why we don't dive into the kinematics? And so let's go in and start. So I have a Cartesian coordinate system, and I will change this to x3. And what I want to do, I want to consider a body of material B, and then that body I'm going to say stretches, and I'm going to say, and let me put the arrow below, stretches, rotates, and distorts into a new body, or into a new deformation of material. So that point P, right, move to point P prime, and that point Q move to say Q prime. So this change, right? And so I'm going to define a coordinate system, and I'm going to use the prime for the deformed configuration, and then I'm going to use x1, x2, and x3 for the undeformed configuration. And I'm going to draw an arrow R that goes from this point to this point, and that I'm going to call R hat. It's a position vector. And then I'm going to draw another vector that goes from this point, and I'll try to draw it from this point to this point, and I'm going to call that R hat prime, okay? And then, and it's just a position vector, nothing more. And then I'm going to track the fact that this point moved to this point. I'm going to call that a deflection. This deflected an amount U tilde, okay? And finally, what I want to look at is that this differential line element, and it's infinitesimal, I'm going to call this dr hat. And in addition to that, or dr, I've been using dr subscript like that. And I apologize for changing convention, but I want to be consistent to the vector notation I've been using. And then this one here, stretched something, some amount, so we'll call it dr prime. Okay, so again, I have a body of material that has stretched and that has deformed a new configuration. And what I want to do is try to understand how the deformation mechanics work. How can I track that? So moving forward, then I'm going to say PQ stretched and rotated to P prime Q prime. And secondly, I'm going to say that R defines position of P, and then R prime defines position of P prime. And I'm going to say that U represents the deflection of from, and you know, I pointed U tilde over here, and I intended to put it from here to here, P. So I'm sorry about that. This right here is U tilde. That's the deflection of point P. I apologize. And to be clear, this position vector is the one here, prime. And then I'm going to draw the arrow a little bit better. Okay. So that's the deflection of point P to P prime. Okay. And so that's really the difference in R and R prime and R. So if I subtract R prime minus R, those two vectors, I should get U. You can see that there. Okay. So now consider, if we consider a nearby point Q in the reference configuration, so in the deformed configuration, the distance PQ in body B is really DL. So if I want to look at this distance, what is this distance? That's DL, and that's squared because the distance is squared, equals DXI DXI. We've used this formula several times now. I can expand it to make it so it looks like something you've seen before. This index notation sometimes is unclear sometimes. But that differential line element is dx1 squared plus dx2 squared plus dx3 squared. And so then after it deforms, I think you all agree with me, after it deforms, PQ changes to P prime Q prime. That line stretched and rotated. And so in the new, and after deformation, that line element now becomes DL prime squared. And I'm going to say is equal to dxi prime dxi prime, where xi prime are the new coordinates of P and Q. And so then I have xi prime equals the components of the vector deflection plus the undeformed coordinates xi. You can also write this in vector notation, x1, x2, x3 prime, prime, prime equals the deflection u1, u2, u3 plus, and that's not a very good bracket, sorry about that, x1, x2, x3. You can see the convenience of using index notation. It just keeps everything very compact and very succinct. And so in other words, the new coordinates xi prime is the deflection that I have in the x direction, in the y direction, the z direction, plus the coordinates xi. And so I can now plug this relationship into here. I'll plug it in there. And so I'll get dxi prime, and that's equal to dxi plus dui. And you can see I just applied a differential operator to this. And you will see here quickly that this requires further derivatives because u of j, sorry, u of I depends, these deflections depend on where you are in the body of material. So ui equals that, and it depends where you are. So therefore, clearly, I need to continue doing a derivative there, plus partial of ui respect to xj dxj. So I can expand dxi prime to look like that. And so I can substitute this relationship into here to figure out what the line element, the new line element dl prime squared is. I want to see what that is. This distance right here, this I want to write it somehow in terms of this dxi's you see. And so then I'll go in and I'll write dl prime squared equals dxi prime, and so all I have to do is substitute the quantity above, and I will go ahead and do that. dxi plus partial ui xj dxj times, and now I have dxi plus partial of ui respect to, I will use a different variable since I use j here, and I'm expanding this, each of this. I'll use a new variable xk dxk, and I will expand that instead. And so I want to define something that right now, I'll define it right now in a minute. But yeah, let's look at how we will approach this. So I'm going to now expand on this more. So I'm going to expand on this more. So I get dxi. If you don't mind, we'll continue here. Plus the partial of ui xj, okay, partial of ui respect to xk, okay, hopefully that's clear so far. Dxj dxk, I think all I'm doing is multiplying everything out, as you can see, plus partial of ui respect to xj, and I have dxi dxj. So I'm basically multiplying this term here, this second term here with the first term there. And then plus partial ui respect to xk dxk, and then I have again multiply against that, so that's txi. So I have four terms from the multiplication, and what I want to do now, I want you to notice that this is dl squared. That's dl squared. So that's my original length here that I had. That's my original length, and so I am basically substituting that, and so that's dl squared. And so I can look at factoring out. I should factor out. I can factor out from here dxm dxn. I'm going to factor it out. And so when I do that, and we should do it, or I will not, I'll do it, but I want to show you that I get the same answer. So let me just go to the next page. So I get dl prime squared equals dl squared, and there's an error here, plus the derivative of ui respect to xm partial ui xn plus derivative um respect to xn plus derivative un respect to xm plus, oh, sorry, no more pluses, we're done there. And this times dxm dxn. I factored it out, and I invite you for extra points to figure out how to do that. And I will show you that I get the same answer. So sorry about that. I should be more clear with my notation so that you can see it well. And I will then take this right here, sorry, and show you that this is the same thing as that. All I've done is factor it out. When I factor these out, factor these out, factor these out, I just use a different variable to factor out. You will have Kronecker delta when you do it. When you factor it out, this is what you get. And so what I want you to notice is that I is a repeated index, so it's summation over I, and that m and n here are not repeated here, but when you multiply against this, yes. Now, I want you to notice that I'm going to call this the twice EMN, and I'm going to call this the Green-Lagrange strain. The Green-Lagrange strain. And so in essence, let's look at one term, for example, in this expansion right here. If I look at one term, so the first term, there's 9 terms when I expand this. When I look at one term, and these for nonlinear deformations, these work for very large deformations. When I expand the first term, what I get is, say, I get twice E11 dx1 dx1 plus etc. I want to just look at the first term to see what happens. 2E11 equals partial of ui respect to x1, ui respect to x1 plus derivative of u1 respect to x1 plus the derivative of u1 respect to x1. This is what you get when you expand that. And so if the rest of the term were 0, say, for whatever reason, then you get dl prime squared equals dl squared plus 2e11 dx1 squared. So you can see here, this is looking at the stretching in just the x direction. And that makes sense that I have this e11 if the rest of the terms were 0. So clearly, if the rest of the terms were 0, then this is what you will get. But in general, then, this is what we call the Green-Lagrange strain tensor, and it has 9 components. Right here, I'm going to now do a little trick that may be confusing, but I'm doing it to save time. So this is mn, and this is mn, and this is mn. I apologize if, yeah, that's correct. And then this is nm. Okay, so in other words, the Green-Lagrange strain tensor is defined as this, and you wonder why is what I've heard back in school that strain is the final length minus original length divided by original length, but this is true for small deformations, and also this is called the engineering strain. So if you've seen this before, this is called the engineering strain. And later I'll show you that the Green-Lagrange strain tensor is the tensor that's for large deformation, and that it will result into that for small deformation. We'll show that a little bit later. I also want you to notice how this expression right here has 9 components of strain. You can see there's 9 components of strain. Because I have m and n as the free indices, and so 3 times 3 is 9. So clearly I have 9 components of strain. And so now I can interchange. Let's interchange m and n. And by the way, what I'm calling the Green-Lagrange strain tensor, let me make sure it's clear. So this is twice EMN. And what I'm calling the Green-Lagrange strain tensor is EMN without the 2. So I apologize for not being clear. So if I can switch m and n here, what I get is the derivative of ui respect to xn, derivative of ui respect to xm, plus the derivative of um respect to xn, plus the derivative of un respect to xm. Well, guess what? These two are equal when you compare them. All we do is switch the order of the different multiplications, and the summation is the same, basically. So in other words, the strain tensor, which is a Green-Lagrange strain tensor, and we'll go into the physical significance of these strain tensors later as we move along. I'm sorry about that. That's a terrible mistake. This is a Green-Lagrange strain tensor, and it's symmetric. The diagonal terms cause stretching of a cube or compression. The off-diagonal terms are the shear strains. So let's continue with this. So going back and understanding what we did, we consider body of material a line element dr PQ, which rotated and translated into P prime Q prime. I define a position vector R to point P. I define a position vector P prime to point P prime. And what I want to do is track and understand what is going on with this line PQ. What is going on there? And then with this position vector R and R prime, I've also defined a vector that goes from point P to P prime to track how it deflects. And so therefore, clearly R prime minus R is equal to U. And I've shown you that here, U equals R prime minus R. And the next thing I did was to figure out this infinitesimal line element PQ and determine that length dr of that dr vector is dl squared equals dxi times dxi. So that's just that. That's index notation. And then I did the same thing here in the deformed configuration, dr prime. And dr prime is dl prime squared, the length, equals dxi prime, And then I related the coordinates. So I basically use this formula here to relate that xi prime, the new coordinates of point P is equal to the deflection u in the x, y, and z directions plus xi, which is the coordinates to this point P. So that's all I have here. I wrote in vector notation so you can see it there. And then what I wanted to do is relate dl prime to dl somehow. And to kind of remove these primes, because they're useless to me. I want to be able to relate it to the undeformed configuration. So then what I did next, I took dl prime, dx prime, I'm sorry, just calculated one of these guys. I expanded it, dxi plus dui, but ui depends on x1, x2, x3. So I did a expansion on that. So it's dxi plus partial ui respect to xj dxj. And I don't know why I have a star here. It's not necessary anymore. So let's keep this clean so you guys can go back and look at this. And then all I did is I substituted this expression back into dl prime squared, and that's all I did here. And notice how I changed the variables from jj to kk. I did that so we don't confuse these two things, because since j was used already for summation once, I don't want to repeat it again. I can use a different variable. And so then I multiply this whole thing, multiply it out, and I'm giving you extra points if you can factor these out successfully. Very easy to factor out using Kronecker delta. And when you do, when you factor it out, you get the dl prime squared equals dl squared plus this Green-Lagrange strain, which is twice Green-Lagrange strain, dxm dxn. And what I notice here is that this is equal to 2e11 dx1 dx1 plus blah, 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 blah. And I get 9 components. I will get 9 of these components. And these guys, these little guys here, what it's telling me is how much strain did it get in that particular direction, dx1, dx1. And so as a consequence, I can then call this coefficient here 2emn. And you're wondering where I have these two. I'll explain it. And EMN is here called the Green-Lagrange strain. And so I define it as this. I showed you that when I do a transpose of MNN, you get this, just the same equation I got here at the top. So the strain tensor is symmetric. There's only 6 components of strain, 3 diagonal terms, 3 off diagonal terms. And I did talk about the engineering strain to remind you that this is different from the engineering strain. The definition you're used to is this one here, and that definition works for small deformations. And so then moving forward then into the different definitions of strain. So engineering strain is what you've seen before. So I'm having some difficulty here. The engineering strain is basically epsilon engineering. And that's equal to L minus L naught divided by L naught. L is the final length of the rod, say. And L naught is the way it started with. So that's L naught, that's L final. And so that's the definition you've probably seen before. And so I'm going to call this L divided by L naught. L is the final length. Let me not use F because by convention that's not used. L divided by L naught, or we can use the definitions I was using before. Sorry for changing the convention on you, but what if we just use the same convention? L prime for the final length, initial length is L. And so if I take this ratio, L prime divided by L minus 1, I'm going to call this a stretch ratio, lambda. Yeah, lambda is what people call it. It's a stretch ratio. And so some other ways to calculate strain is this true strain. Here, the true strain is calculated so that the epsilon true strain is a little bit different. It's the final length minus the initial length divided by the final length. And the final length is always changing. So it could be difficult to calculate, but it is 1 minus L divided by L prime, and this is basically 1 minus 1 over lambda. So that's another way to define this. We also have then what I just discussed. These two strain approaches you've seen before. You should have seen these in the mechanics and materials class. But I'm covering this because I know there's other areas of discipline taking my class this year. And to be respectful to them, I'm covering some fundamental ideas. The green strain is measured as half of the difference in the of the squares of the deformed and undeformed lengths divided by the square of the undeformed length. And you may wonder why I'm doing that. And it turns out, and it's a long story, it's a long story, but this strain happens to be energetically conjugate to the first Piola-Kirchhoff stress. I won't be covering all that today, but I want to just bring this to attention. This strain is very convenient because it is energetically conjugate to, to a stress measure that's significantly used in industry. Um, and so continuing forward, that uh, the Lagrange or green strain is written usually as E equals 1/2. So this is one, measurement two, measurement three, and you get 1/2 L prime squared minus L squared divided by L squared. Okay, and this gives you 1/2 of the stretch squared minus 1. Now, this is just a simple definition if I just had a rod, right? But the real definition is this one. This is the most comprehensive and more general. I'm just showing you if I had a rod, what it will look like. So if I had a rod of length L and L, and then it deformed an amount L prime. So then that's what this formula would look like. So the Lagrangian way of formulating the strain has the same spirit. It has the same spirit. You can see it has the same spirit as the, there's a green strain. Let me write it here. It has the same spirit as the engineering strain. And in that sense, the length is found by comparing to the original length, because in both cases, I'm looking at the denominator as original length. And you can see that when the length in change, the change in length is really small. When the length in change is really small, you can demonstrate that this is very close to, I'm sorry, when the change in length is very small, that means that lambda minus 1 will be much less than 1. You will see that. So when that happens, then that may explain why I have this mysterious factor of 2 then. And if I were to take this expression and I were to factor it, so lambda minus 1 times lambda plus 1, you can see that when the stretch is very near unity, very close to 1, that lambda plus 1 becomes 2. So lambda becomes close to 1, right? So lambda is close to 1. So I may have a problem with what I wrote. So if lambda is close to, what I meant to say is when lambda minus 1 is close to 0, so it's infinitesimal. Infinitesimal. That's what I should have said. Because if I have 1.001, then this is close to 0. So that's what I meant to say. When lambda is very small, when the stretch is very small, right? So when it's close to unity, then this is closer to, you can see that. And when that happens, I really need a way of getting, okay, just a second. So continuing forward, I apologize, we're okay. Good news, we're okay. If lambda is close to unity, then that's close to 2. 2 cancels out, and then E becomes close to lambda minus 1. So this becomes approximately to lambda minus 1, which is what engineering strain is for small deformations. So clearly works, and that's why I need the 2 there for this to work out as an example, okay? As an example. That's why it works out nicely. And so with that said, so let me explain one more time why the 1/2 is there. Engineering strain is defined as this, and I get lambda minus 1. If this is close, if the engineering strain is very small for small deformations, and lambda was close to 1, say close to 1, then then 1 plus 1 is 2, is near 2. And so I want the large deformation, this is a large deformation green strain, to be close to this strain here for small deformations, for small strains. And so the 2 and 2 cancel out, and I get lambda minus 1 for small deformation. And so that's why I need the 2 there. Otherwise, what I'll get is lambda minus 1, and I'll get it times 2 instead. And that's not what I get here. So it needs to be consistent for small and large deformations. And so that's why the 1/2 is here. The second question is, why is it squared? Is the way that the green strain is defined, but not just that, it can be proven that the green Lagrange strain is energetically conjugate to the Piola-Kirchhoff stress, which is another stress measure. It's another stress measure I haven't discussed. And now what we're going to discuss is the idea of the deformation gradient. Here, when I look at the deformation here, let me go to this formula right here. I can define a deformation gradient, and I can factor out dxm to look at that. So this dxm, I'll factor out dxm out of here. And when I factor it out, I get del im plus, okay, derivative ui respect to xm. So I can factor it out. And when I do that, this coefficient here really represents the deformation gradient. I'm going to call it F. So I'm going to call this F. That's a deformation gradient. And I'm going to call this FIM. And note, I want you to note that FIM is not equal to FMI. You can see that very clearly. You cannot just switch I and M and get the same thing. You don't. And I'll expand it for you in the very next page. So why don't you take a screenshot of this, put it in PowerPoint. Let me go now. So take a screenshot now with a snipping tool within your computer, because I'm going to take this expression right now, and I'm going to show you what it looks like when I expand it out. And when I do, I get that F equals 1 plus derivative u1 respect to x1. Okay, derivative u1 respect to x2. Derivative u1 respect to x3. And then here I get derivative u2 respect to x1. So clearly the off diagonal terms are not the same. But 1 plus derivative u2 respect to x2. And then here I get derivative u2 respect to x3. Derivative u3 respect to x1. Derivative u3 respect to x2. And then here I get 1 plus derivative u3 respect to x3. So that's what I get for deformation gradients. And that deformation gradient is very useful, and I'll be talking about that. We can express the green Lagrange strains in terms of this deformation gradient. That's why it's so useful. So this deformation gradient F, we can actually use it for something useful. And so if I were to calculate E, so E is a tensor. E is a tensor. It actually is 1/2 F transpose F minus the identity matrix. I will get the same answer as I did here. Okay, I'll get the same thing you see here, the same thing, which is very powerful because you can quickly calculate this thing. But the deformation gradient is also very useful because it tells you how these lines stretch in a particular direction. They tell you how things are deforming, and that's why this stretch F is so useful. It gives you a lot of information about the material, how the material deforms. And so the green Lagrange strains can be expressed as a function of the deformation gradient tensor and are basically referred and they're framed upon the undeformed body. Basically, we're taking partial derivatives in the coordinate system of this one, of the undeformed body. So I'm tracking everything back to the undeformed body. That's really what I'm doing. And it's a very useful quantity. I'll be explaining very soon what these things really mean physically, because I think it adds a lot of value understanding that. Okay. So let's continue then with that. Okay, so let's look at the volume change. We can also look at volume change. The volume change, so say I want to calculate the volume change. Simply put, you can do that. And the formula for that is dv star. So if I have a cube of element that has deformed, distorted, and stretched, it's going to be the determinant of f times dv. And that can be proven very easily, but we won't do the proof in this course because the purpose of this course is to cover approximation theories. I'm just letting you know that this formula does work really well for calculating the, so basically if you can calculate this right here, you can calculate the volume change for the infinitesimal element that looks like a cube. So now let's try to understand the physics. Let's try to understand the physics of what we're talking about here. Very important, very important. So let's start with stretch. Let's start with the idea of stretch. And let me show you how to apply what we learned. So let's say I have the coordinates of the deformed configuration. And say that the deformed configuration is x1, and then I have x1 prime for the deformed, x2 for the undeformed, and x2 prime for the deformed. And then I have a little square. And I want to look at stretch, but stretch going that way, in this direction. Okay, so that's what I want to look at. Let me call this length A, and let me call this stretch amount E. Okay, let's look at that. You should be able to calculate the engineering strain. We'll do it later. But let's look at the new coordinates. Okay, so this point here, we know this point here, we know this point here very well. So we can calculate coordinates for everything. But the formula for the deformation of this little square here into this rectangle is really x1 prime x1 plus e over a x2. And then I have x2 equals x3. x2 prime equals x2, and then we have x3 prime equals x3. Let's see if that works. You can see here that what we're saying here, let's look at this. So if I plug in for x2, let's plug in, actually let's plug in this coordinate here, 0. So this a comma 0. If I plug it in here, you find that I get a plus 0, sorry. So I have the coordinates here of x1 is a, and I have a problem, and I'm glad I checked it because this should be x1. So let's try to plug it in now. x1 prime, if I plug this point here, I get a plus e over a equals times a equals a plus e. So the new coordinates here of this point is a plus e, and you can see it works out. Clearly, in this particular point, s2 prime is 0, so that point stays there. And I'm not looking at anything out of plane, so that makes sense that that's 0. So let's look at this point now to see where it moves to. x1 prime equals, that coordinate there is what? That's a comma a. So the same thing, a plus e over a times a, that's a plus e. That isn't that the coordinates of this point, a plus e. And then x2 prime is x2, but x2 in this, for this particular point is a, and so obviously this is a. So it works out. You can see that it works out, and we found it. We found what that coordinate is. Now, if you wanted to look at engineering strain, let's just do that for a second to see what you get. Isn't it the final length minus the original length? So the final length is e plus a minus the original length is a divided by original length is A. So you get E plus A minus A, that's E over A. That's what I get. And yeah, so that's what I got. Okay. And that's the engineering strain I get. So let's calculate the Green-Lagrange strain. But to do that, I should first calculate the deflections in terms of X. So I have U1 equals X1 prime minus X1, and that's equal to E over A X1 by using this formula here. U2 is 0 because X2 prime minus X2 is 0. So clearly there's no deflection in that direction. You can see that happening with this square, nothing's happening. And I have U3 equals 0. So very nice. We were able to find what that is. And now I can calculate each of the Green-Lagrange strain. So let's try one by one. E11 is, and let me write the formula here for you one more time. EMN is, and then we can expand it. Partial UI respect to XM, partial UJ respect to XN, plus partial of U. Forgive me. Give me a minute. And so then we have UM. Sorry, I'm having some difficulty here. UM XN plus UN XM times 1/2. And let's see if that matches what I had before because I'm going by memory. Okay. We have, yeah, we got it right. So everything is correct. So let's calculate E11. E11 is 1/2. And you can see here this derivative of U1 respect to X1 plus derivative of U2 respect to X1 plus derivative of U1 respect to X3. Not X3, I don't know why I said that, 1. So I'm just expanding. This is 0, and this is 0 because U2 and U3 are 0. And I know what derivative of U1 respect to X1 is, that's E over A. And E over A is multiplied twice, so that's E over A squared. And this right here is twice E over A. So then I get, for that, I get E over A plus 1/2 E over A squared. Now, we can calculate the other ones, but I'll stop here for now. I can keep calculating more strains if I wanted to, but I will stop here for now. I can calculate E22, E33. E22 most likely will be 0, E33. You can calculate all of them very successfully. And yeah, so all of them should be 0, most likely, but you should try it at home to see if that's true. If I have infinitesimal stretch, like it's stretching very small amount, then E over A is small. So small, so say small, then E over A squared should be close to 0. Because if E over A is very small, then something very small squared should be close to 0. So therefore, E11 approaches E over A for, because this goes away basically, for small stretches. And you can see that I got the same answer as I got for the engineering strain. You can see that it worked out very nicely. In fact, it worked so nice. I'm very happy about it. So can I ask? Okay, so I did make a mistake. Thank you so much for correcting me. This is supposed to be I and not J. So thank you. So it's derivative UI respect to XN. So that's I. So let's look at what happens. Let's calculate the stretch. So say I have a vector here. I want to calculate how much this stretches. A unit vector that I want to look at there. So to calculate the stretch, what I can do, I can calculate lambda squared, and it's going to depend on the direction because I could select a vector n that's pointed like that too. So if I want to look what the stretch of that is, I need to really know what vector that is. So the stretch definitely depends on the direction of n. And that can be calculated as the deformation gradient, okay, times n. And if I want to find what it is, I have to get the dot product of this with respect to that. So basically I have to multiply it by itself. In our scenario, we can calculate f very quickly. So what is f? Let's calculate f. Can somebody help me looking at this formula? Can you see that this is 0? This is right. Can you see that this term is 0, this term is 0, this diagonal term is 1, 1, off diagonal terms are 0, and I'm left with 1 plus the derivative of u1 with respect to x1, and the derivative of u1 with respect to x1 was found to be e over a. So I have 1 plus e over a as a diagonal term. And then these remaining ones are like that. And so now the vector n that I chose was very nice because it's a unit vector, it's pointed to the right. And I'm going to use that vector to be n, and I'll just say 1, 0, 0. So that makes it very easy. So let's do that calculation. So what do I get? I get, yeah, that multiplication is just 1 plus e over a, right? E1 dotted with 1 plus e over a E1, isn't it? Right? I mean, all you have to do is multiply f times n to figure out that that's what you get. And that's basically 1 plus e over a squared. And so the stretch for that direction is 1 plus e over a for this example. And we're in here in the square, the way I defined it, n is pointed that way, and it's a unit vector that I chose, 1, 0, 0. You also want to choose a unit vector. So that one is the one I chose to see how much is stretched. So that's what I got. That's a stretch that I got. What else we have? What else can we discuss? So that's a stretch I got for that problem. And yeah, so that's how you calculate the stretch for this particular line element. You can see here that this is equal to a plus e divided by a. So if I were to look at it physically, this started with a length a, and it ended slightly longer. And this is e. So in other words, the stretch ratio, which is a ratio, is basically the final length divided by the original length. And that's what we had to define it as before, if you recall. So let's go back. So I defined the stretch to be the final length divided by the original length, lambda. And so it is consistent. You can see it's consistent and it works very well. Now, if I were to take another vector and I chose a vector that was pointed, say, in a different direction, the answer may not be as obvious if I chose a vector like that. So that's why you want to perform this calculation, because the stretch is going to depend upon which direction you're looking at. Okay, so does so let's look at the situation of pure shear now. And so I want to look at what is going on there. So I have x1 prime again for the deformed, and for the undeformed I have x1, x2, and for the deform x2 prime, and the square has deformed to this shape, and this length here is E, and this height is A, and this width is A, okay? And we're gonna say that the thickness direction, whatever is going on there, is negligible for now. So I'm not gonna focus on the thickness direction, although you can do that. And so let's start with x1 prime equals x1 plus E over A, x2, and then I have, and I'm gonna do it differently this time, if you don't mind. And then I have x2 prime equals x2, and x3 prime is x3, which means, this means that u2 and u3 are 0, clearly. There's no, you can see that happening. There's no deflection going up, and there's no deflection going out of plane. So that's the only one that survives is u1, and so u1 is x1 prime minus x1, which is E over A, x2. So that's what we get. You know, one thing we could do to calculate all the Lagrange strains really quickly is to use the formula F transpose F minus the identity matrix. I could do that. Why we don't use a different formula instead of calculating it using this formula, which is fine. We can use this formula, but you know, you can see that it takes time. So why not just do this calculation here and see what happens? So for our problem, I believe that all these terms are 0. This term, this term, this term, this term, this term, this term is 0. So that's diagonal term is 1. The only thing that survives is probably this term here, and this term there. So let's see what we get. 1, and everything else should be 0. 0, 0, 0, 0, 0, 0. So the only thing, two terms is the top two, and the diagonal terms being 1. So derivative u1 with respect to x1. Do I have a derivative u1 with respect to x1 here? No, because u1 does not depend on x1. So that f, let me calculate f first. So f is, that's 0, and this term is E over A. That's 0, 0, 1, 0, 0, 0, 1. I'll appreciate if somebody checked what I have. I wish that we could check it quick. You know, that diagonal term is not 0, it's 1. Because the derivative of u1 with respect to x1 is 1, but it had 0, but it has 1 plus. So that stays there. And if this is incorrect, the rest will be incorrect. So hopefully we have it correct. And then we have 1 E over A 0. So I'm doing a different way, guys. I can use index notation. I can just do it all at once. There are two ways of doing it. And we just want to get to the answer as quick as we can so we can keep learning new material, because this class is really exciting, just extremely exciting. And then minus the identity matrix. I'll just be lazy and put Kronecker delta, and at the end we'll just subtract 1, 1, 1 out of it. So let's multiply this. That's 1. That's E over A. That's 0. That's E over A. That's E over A squared plus 1. And this is 0. No. So yeah, that's 0. That's 0. That's 0. That's 1. And now I have to subtract the identity matrix. And I have 1, I have 0, E over A, 0, E over A, E over A squared. That's interesting, that E over A squared, check it out, 0, 0, 0, 1. Okay, and one thing I want to point out is that I am missing something here, and the definition of strain in that manner was provided to you as with a 1/2, which I have forgotten to add into what I did. So why we don't just add the 1/2 there? Like, we'll just slip it in there, slip it in here, and here. And then now we basically have E over 2A, which is do it correctly. E over 2A. You can see the strain tensor is symmetric, although the deformation gradient was not symmetric. It turned out to be symmetric at the end. And there's a 1/2 here, which is very interesting. That's very interesting, that one that we got there. And so that's E11, E12, E13, E21, E22, E23, E31, E32, E33. So, and that's wrong. This one is 0 also. So this strain is 0, that 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 strain is 0. And this is very interesting because E22 is not 0. E22 is 1/2 EA squared, meaning there's something going on in this direction. So in other words, if I were to have a vector pointed that way, this is telling me that that vector will stretch in that direction somehow. And you can see that it must be stretching because this line here increase in length in the deformed configuration. So clearly something happened there that should be considered, and we can see that something is going on. Something is going on there that we want to learn more about. So that is very cool that we found it. Now we found the shear strain as well, and the shear strain is just simply E12, E12. Can you hear me now? Yeah. I was talking for like 10 minutes. No, 2 minutes. Let me just a second. So for small angle alpha, tangent of alpha is close to alpha. And we just showed that this is E over A. So when I examine the definition of E12, which I got to be 1/2 E over A, twice of E1 over 2 is E over A. And so this represents, in fact, the angle change. So twice E1 over 2 becomes the angle change because it went from 90 degrees to a different angle here, 90 minus alpha. And so clearly the interpretation of 2E12 is the angle change. So very interesting idea to examine. And so now let's look at calculating. Let's calculate now. What is going on? So say I'm interested in determining, I have two vectors I started with, and I want to know what is going on with that angle. So we can compute the angle between the deformed tangent vectors to figure out what is going on there. So if this was N1 and this is N2, then I can use the definition of that we've seen before. You've seen this before. Cosine and the angle between two vectors is, and then you take the dot product of these two vectors, and then you take the magnitude of them. Very similarly now, I can just take the dot product of the deformation gradient F of vector 1 with N2, and then I'll find its magnitude. So I'll find the magnitude of that. Like that. And that way I can find the angle between them in the deformed state. So say, presume for a second, I started with this vector and that vector, and this vector is N1, and this vector is N2. And so now I know the deformation gradient F because I calculated that. The deformation gradient F was given by this. So all I have to do is multiply that together. And I calculated that to be this. And I'm just checking I got it right, that I have correctly transcribed F. And I did. So then I take times N1, which is 1, 0, 0. And then the dot product of 1 E over A, 0, 0, 1, 0, 0, 0, 1. And here in this case, I have 0, 1, 0. And now I'll take the magnitude of whatever I get here. Sorry about that. And that's the cosine in the deformed state between F and 1 and F and 2. And so to continue, the first one gives me 1. And that's dotted with E over A, 1, 0. And then the magnitude is of this vector is 1. So I get 1 for the magnitude of the vector above. And the magnitude of this vector below, the second one here, is E. So the square root Sorry about that. And so when I multiply the stuff above, I get E times A. And that's it. And then at the bottom, I get 1 E over A squared plus 1. If I multiply everything by A, I get E squared plus A squared. That's what I get for the cosine between these two. But that's interesting because if I look at what I had earlier, so let's look at that's a cosine in a deformed state. The cosine here is giving us the angle between these two vectors in the deformed configuration. And this is the number we got. So what we want to do is visualize what's happened there. So this is what I got. And this vector N1 and 2, we've been able to find what is the angle in between. Now N2 has moved like that due to the F, the gradient F, multiplied by N2 has caused the vector to stretch. And this vector F N1, I believe if you calculate this, it's going to show that this vector does not stretch, stays the same. And this is the angle we just calculated. So that's that cosine, let me call it alpha. That cosine of alpha has been found to be E divided by E squared plus A squared. And if we look here carefully, and I draw a straight line here, this angle alpha is the same angle as this alpha. So in reality, this is E, this is A, so this is the hypotenuse, E squared plus A squared. And so in fact, what we found is that now we can find the change in angle here, beta. And that change in angle can be quickly found by tangent beta equals E over A. So this is exactly what we got, but we did it with the definition of the deformation gradient. So really good, we're able to make progress there. The second thing I want to mention is the small strain approximation. So the green Lagrange strain tensor was shown to be EIJ equals 1/2 derivative of UM XI derivative of UM XJ plus derivative of UI respect to XJ plus derivative of UJ respect to XI. And what we find is that here is that if we find that this here, this derivative u L respect to xn, if this is small, less than 1, much smaller than 1, then what we're going to find is that this multiplication, let's say this is close, it is small, right? So those gradients are small, then this multiplication will be close to 0, right? Because if this was 0.01, then this multiplication will be very close to 10 to the minus 4. Okay, as an example. So small strain approximation then will lead, and this is true for composites, a lot of composite materials, a lot of applications. And when you design, you don't want things to go plastic. So typically the strains you're designing for are going to be in the small deformation range. But EIJ becomes small strain approximation. Epsilon is what's used typically. And we get 1/2 the derivative I respect to xj plus uj respect to xi. And I can now check that they have 6 components of strain because if I do epsilon ij, That is equal to epsilon ji, no change there. You can see that the indices just swap and you get the same answer. And also let's look at epsilon 1, 1. So epsilon 1, 1 is 1/2 derivative u1 respect to x1 plus derivative u1 respect to x1. And in fact, you get the same value. Epsilon 2, 2 derivative u2 respect to x2. Epsilon 3, 3 is the derivative u3 respect to x3. And these string components are normal to the cube space and causes stretching or compression. And then we have these strings here. Twice epsilon 1, 2 is the derivative u1 respect to x2 plus derivative u2 respect to x1. And this represents the angle change as shown earlier. And it's a shear. This is shear strain. Twice epsilon 1, 3. And again, angle change. And then finally, I have twice epsilon 2, 3. And this is all angle change here. So 6 components of strain, and they're small. And so now let's look at volume change of an infinitesimal cube. And if I have a cube of material, there's dx1, dx2, and dx3 after deformation, you'll get dx1 prime and so the volume in the deformed configuration is dv prime, like that. And when I can expand, I know what dx1 prime is. We did it earlier, so that's dx1 plus partial of derivative u1 respect to xj dxj times dx2 plus derivative u2 respect to xk dxk, and then dx3 plus derivative u3 respect to x3 d, and then not x3, but we're expanding on u3, so that's going to be partial of xl dxl. And my next step is to multiply everything out. I can also factor out dx1 out of here and dx2 and dx3. So when I do that, I get dx1, dx2, and dx3. And that leaves me with 1 plus partial u1 respect to x1, 1 plus partial u2 respect to x2, plus 1 times this times